So I'm Nick Pentreath, MLNick on Twitter and GitHub. I'm a principal engineer at IBM. So I work for a team which is mostly based out of San Francisco called Code. That's a center for open source data and AI technologies. I focus on machine learning and artificial intelligence. I've had a long background in the Apache Spark project, where I'm a committer and PMC member, author of a very out-of-date book on machine learning with Spark, if you're interested in that. And I present at various events, meetups, conferences, and so on around the world about machine learning. So a little bit about Code, Center for Open Source Data and AI Technologies. It's a team at IBM based out of San Francisco, but we now have team members all over the world, including Cape Town and Switzerland and the rest of the US. We're about 36 open source developers focused on the end-to-end enterprise AI lifecycle out in open source. So this evolved out of a center focused on Apache Spark, which is when I joined. But since then, we have expanded that focus to look at the path and data science ecosystem. Of course, Apache Spark is still a big part of that, as well as more recently deep learning, so all the usual frameworks. And two projects that I'm going to talk about today, mostly the Model Asset Exchange and also the Fabric for Deep Learning, which is a project that comes out of IBM Research. We also curate some IBM Research collaborative projects that came out of both product and research groups for adversarial robustness and AI fairness. And I do a lot of work around open source machine learning standards for deployment. So the perception of applying the deep learning model is, generally speaking, that you start with data and you either train it, if you're a data scientist and you have the expertise, you just train it using your framework, and then you profit from it, right? You get benefit. And if you are deploying that model, you take a pre-trained model that's out there, you go and find it, you just simply deploy it, and again, profit, benefit. But the reality is a lot more complex. So you have to go through all of these phases to get to that end solution where you can actually use the model. And we break these down really into three sub-phases. The first is discovery. Second is the execution, you're actually training or deploying. And the third is consumption. How do you go and use that model and to do something useful? So in discovery, you've got to start off and you're going to go find that model first of all, right? So if there's a use case that you want to solve, a problem you want to solve, you may either have a data science team and the resources to go and find a model that you want to train on custom data, or you may be an application developer or a scientist who doesn't necessarily have either the time or the resources to go and train a model, but you may want to find something that has hopefully been trained already for you that you can use. So first of all, you've got to go and find out whether that even exists. So if you're looking, for example, for an image classifier for deep learning, you're going to get a whole bunch of hits, right? And you've got to go through and you've got to read this paper and this paper and this paper and this paper and this paper. And by then, you might have a reasonable overview of what's going on. And you've got to figure out what is the state of the art. Does it actually do what you need? What data set was it trained on if it's a pre-trained model? What kind of classes and objects can it recognize? Does it meet the need? The second major sort of problem or question that you have to answer is, can you use that, right? So if it's been published out in open source in an academic paper, typically, yes, it's out in the public domain in some form, but what are the potential licensing issues around that model, that piece of research? In some cases, it's, there are restrictions. And then thirdly, is it performant enough? So is that classification performance going to meet your business use case and requirements? So once you've done that, okay, you found a paper. Now, you may be able to go and implement that from scratch. If you have the data science and machine learning expertise, like many of you in the room might do that. But in many cases, you don't have that expertise. Or even if you do, it's a cost-benefit trade-off, right? Do you want to spend all that time training a model or building your own model from scratch if there's something out there that already exists? And most of the time, there is code out there, right? There's an implementation for training code. In many cases, there are pre-trained models on standardized data sets, public data sets. But again, you have to go and find the one that actually does what you need. So it's trained on a data set that has the classes you need, for example. It is a state-of-the-art implementation. It's in the framework that you might care about. And again, you have to go and check the licensing issues around this. So there's licenses attached to data sets, there's licenses attached to pre-trained weights and to model code, training code. And they can all be different. And in many cases, you might have a data set that is restricted use, so maybe it can only be used for non-commercial purposes, maybe research purposes. Hopefully, it's like a Creative Commons thing where you can just use it. But in many cases, other groups, research groups, have gone out and trained large models, let's say, on ImageNet. And ImageNet itself might be research purposes only, so you, as a commercial entity, couldn't go and train a model. But helpfully, someone at Google has, researchers trained a model and released the weights, and they're under an Apache license. So hopefully that ticks the box and you can go and use it, right? But you still have to do that investigation and understand the lineage and understand where the legal issues lie. And then finally, is it performant enough? Is it meeting the requirements for your classification accuracy? You don't necessarily know that out the box for your particular problem. So once you've gone and found that model and you've got the one that you want to use, you still have to verify these things. So they may claim on the paper that achieves some sort of performance. They may claim on the GitHub repo that it is a faithful implementation of the paper, but how do you know? Right? The only way you can know is to go and dive into the code and test it. And you need to test it on potentially your own data set, your own custom data if you want to apply that model, as well as obviously the data set it was trained on. You have to check the code quality and correctness. Now, a lot of the time, these kind of models are coming out of research labs, so really great quality academic research, not always the best quality in terms of code. Quality, coverage, test coverage, modularization, the ability to actually change things. And yes, bugs do often exist, right? Thirdly, licensing. So you need very specific licensing terms most of the time for a commercial use application. And again, there might be some claims in the code, somewhere on the paper, in the GitHub repo, in the README, but you still need to verify and check that these are all correct and that you can actually use this model. And finally, for both computation efficiency as well as accuracy, you need to check performance. Is it doing what you think it is and what it claims? So once you have passed that discovery phase and you've done all these steps, which is quite a lot of work, you then either need to train the model if you're training from scratch or doing transfer learning, and then deploy it, either deploy the pre-trained model that you found if you don't want to do the training part or can't for some reason, or you train the model and then you deploy what you just trained. So the trained model is essentially a combination of these four things. You've got the data, the model, code itself, the architecture, compute resources, in some cases pretty significant, and days and weeks of training time, and the expertise to go and fine-tune that model, do hyperparameter optimization, architecture, search, and deciding what specific architecture you're going to apply. And then at the end of that, you come up with a trained model. For deploying, you essentially have to take that pre-trained model, that trained model that you've just created, and package it up in some way and deploy it to your serving environment. Often, the code that may be out there on GitHub, for example, is optimized for batch inference, because when training, that's what you need. But the code path for single instance inference sometimes doesn't even exist, right? So in many cases, you actually have to go and write that. And you have to customize what is out there. So finally, you have a deployed model, but you actually have to integrate it into an application. Now, most of the time, your application doesn't know what a tensor is, and it doesn't care, right? Your end user, your business user, your application developer in your organization, or if it's you don't really care that your TensorFlow model spits out a tensor representation of class probabilities. What you care about is a application usable, human usable, and readable variant of that. So typically, this will be a piece of JSON that tells you, yes, here's a probability of a class, but I need the class labels because I might want to annotate a returned image to a user, or I might want to surface that up in the application, or I just might want to understand what is going on. So those are, at a high level, the challenges that are involved in just getting a kind of commonly used or state-of-the-art machine learning model through that process into production and actually using it. So we'll just walk through a little bit some of the particular challenges at each phase. So first in discovery, right, well, you might say, well, that's a solved problem. I mean, there are model zoos out there, right? Model zoo is a nice, organized place where you can go and look up what you need, and it's all categorized, you know, and standardized and easy to navigate, right? Wrong. Okay, a model zoo looks more like this in practice. So in order to find what you need to dig through this pile of, you know, papers and books, and hopefully it's in there. And even if it is, maybe the page you need has been torn out, right? So that's in practice. So just that discovery phase, the existing tools out there, you know, are pretty deficient. So when it comes to execution, you have to solve this training and deployment problem. And for training, you know, just like there are many ways to go and train your body in the gym or, you know, out on the running or whatever it is, there are just as many ways of training deep learning models. So yes, the problem is solved, but the problem is solved in umpteen different ways. And each of these frameworks you know, does training in a different way, it has a different way of handling distributed training, it has a different way of, you know, reading in data, of serializing models, of accessing GPUs, all of these kind of things. And yes, it's gotten a lot easier with high-level APIs and Keras and PyTorch and, you know, now TensorFlow 2.0. But effectively, in any kind of small to even, well, medium to large size organization, or even a small one, you are going to encounter almost all of these, and you actually have to support them all. You know, you have to be able to give data scientists and machine learning engineers and researchers the tools that they know and love. So you can't just typically, unfortunately, settle just on one. You need to support them all. So for deployment, that is you know, a whole talk in itself, which I sometimes do on ML deployment. But in many ways, containerization has, you know, standardized this for software deployment in general, and the same is true for machine learning. So container-based deployment gives us a lot of benefits. You know, you have repeatability and certainty. You know, if something works on your laptop and you package it up and you deploy it to Cube, you know, it typically works. And what I think is the key benefit here is the separation of concerns. So your data scientists and your machine learning engineers and the researchers can focus on the what. You know, they can focus on what model they're building and not really worry about, you know, the how it's going to get deployed to the serving environment. Your production engineers can just run the Kubernetes cluster, you know, manage the configurations, and all they have to do is, you know, take a container, right? So that is part of the story, but the what is still important, right? Because what goes in the container makes a difference. So, for example, performance. You know, yes, you know, a Python model that is mostly TensorFlow running on the GPU, or mostly PyTorch, or mostly even NumPy, scikit-learn, is hopefully going to be pretty performant. But if it's just Python code that you're plunking into a container, it may not be. If it's an R model, it may not be, right? So performance is really very variable across these dimensions of different, you know, what framework and what code is used. It requires good, you know, CI DevOps practices to get that pipeline running. And the key issue is it doesn't solve this issue of standardization, this problem, right? So how does the business, how do the other applications, how do the other microservices interact with that model that's deployed? If it's just a container, you know, how do you call it? What is the data format? What is the specification? So there's still this question of what formats and APIs are exposed. How do we standardize that? And then finally, for consumption. So for consumability, you know, the analogy I always like to use is the telephone, right? So we all know what a telephone is. You know, at IBM, for example, everyone knows how to use a telephone, and everyone uses a telephone in their day-to-day job. But IBM is not a phone company. We are not phone experts, right? So how do we make machine learning and deep learning as consumable as a telephone? And one of the solutions, or part of the solution, is this concept of APIs, right? This interface. Now, all of these phones are, to all intents and purposes, the same. Okay, maybe the top left one, you know, you may never have seen if you're like really young, but generally speaking, if you know how to dial a phone, you're going to be able to use all of these because the interface, the way you dial a phone number, is standardized across all of those different phones. So this concept of standardization, consumability, and trying to make deep learning accessible and easy to use is really what's behind the Model Asset Exchange. So this is a project that I've been working on for a while now, about a year, with a small team. And it is a collection, a one-stop shop of free and open source deep learning models. So we cover a wide variety of domains, vision, NLP, speech, audio, video recognition. And the idea is to bring best of breed, state-of-the-art, well-known, cited models, well-known good implementations of them, and package them up in a standardized format. So we vet the code, we vet the licensing, so you can be sure that it's usable in your application, you can be sure that it works, and that it's performant. And that can be packaged up, deployed as a Docker container with one line of code, deployed to Kubernetes, or for the trainable models, which is, I'll talk a little bit about, and it's still a work in progress. You can train that on either the Fabric for Deep Learning, which is one of the IBM projects, open source projects that I'll talk about a little bit, or on Watson's machine learning service, which is our cloud-based product for training and deploying models. So I should hopefully have time to go through a little demo later, but the idea behind Max is to have all of this metadata exposed in an easy-to-use format. So you can see all the licensing. You can very quickly check what the licenses applicable to all the different pieces are, the model code, the model weights, the data set obviously for trainable models. What data was it trained on? What is the format, the framework? As well as more recently, we started to expound upon this benchmarking section of the model, so you can quickly see what is the state-of-the-art performance, what is the performance on the model, on the data set it was trained on. For this particular sentiment classifier, what is how does it generalize across different types of data sets, to try and get a sense of what does this model actually meet your requirements. So I briefly mentioned the Fabric for Deep Learning. I don't have that much time, so I won't go into too much detail, but Fabric for Deep Learning, or FIDDLE, is a project that came out of IBM Research and the Deep Learning as a Service product group, and is now open sourced. And it is a framework that runs on top of Kubernetes, and it enables multi-framework or framework-agnostic training of deep learning models in a distributed fashion. So you can train TensorFlow, Keras, PyTorch, Caffe. Now it supports H2O.ai for kind of more traditional machine learning models. And you can do that in an agnostic way. So all you have to do is package up your training code. You create a model definition via YAML. You submit that to the cluster, and it takes care of everything for you. So it'll spin up nodes, and it'll distribute the training and handle GPU resource allocation, all the things that as a data scientist you really shouldn't be caring about. The framework will handle all of that for you. It also supports model serving via Selden, distributed trading via Horomod out of Uber. So you can check it out at the links there. So for Max, getting started for trainable models is as easy as getting your custom training data, your training code, and that training definition, packaging everything up as a standardized script, and then training it on FIDDLE or the Watson machine learning service. And for a deployable model, we've effectively taken care of that initial step of combining those elements into a pre-trained model. But what Max gives you is standardized input and output processing. So we take the raw input, pre-process it, feed it through the inference, and you get back a post-processed output that is a usable JSON blob that you can use in an application or downstream. And you get a standardized REST API with a Swagger definition. So you can deploy that as a microservice, either locally on Docker, using Docker, or on your Kube cluster on whatever on-premises or cloud you happen to be using. So you get a standardized inference endpoint, metadata endpoint, Swagger specification that can be used to generate auto-generate code clients, for example. Okay, so this is the Model Asset Exchange. You can hit that link that there's in the presentation, and you can see there's a whole bunch of models on here. So if I go to one of them, for example, the object detection model, you get a whole bunch of options at the top where you can go to the GitHub page for that model. So everything you see here is completely free and open source. The licenses are all good for you to use. You can try the API. You get an overview of You get an overview of that model metadata, the references, the licenses, that one-line deployment on Kube or locally. And more recently, you can even deploy it in a Node Redflow, which is a drag-and-drop code-free internet IoT platform. So you can use it in your IoT apps. And then for many of the models, we have created either embedded in the model or as an external kind of code pattern tutorial, an example application which just shows you, you can choose a file, submit an image for this object detector, for example, and hopefully it will pick up a couple of things. Yeah, so this one has found a donut, so at least it's got something, not quite a donut, but we can play around with probability thresholds and see a couple of donuts. So it I don't think it's got croissant in the ImageNet data set, maybe. These are really examples to try and illustrate, in particular for application developers who are not that familiar necessarily with deep learning and machine learning, how to actually integrate that in a very easy way into the application. So you don't need to know anything about the model, you just need to know about REST APIs, which is what developers live and breathe on the web every day. So in summary, at the moment we have 30 models, 4 of which are trainable, so that's something that we're working on currently, is to have a lot more models that are trainable on your own data. We cover a wide variety of use cases, these code patterns and tutorials and blog posts and videos and a bunch of resources to take you all the way through, from the basics of how to use Max, if you are an app developer who has a little experience, all the way through to the more complex stuff if you are experienced. You can have this one-line deployment to Docker and Kube. We've released a Max API framework, which is just a very lightweight Python framework for wrapping the models. And in the future, a lot more to come. So predominantly, we'll be looking to make these deployable to Watson's machine learning service. So if you want a managed solution for deploying models, as well as train existing deployable models on your own custom data. So do transfer learning on custom object detection, data sets, image segmentation, and so on. And a lot more Max-related content. So you'll see us, the team, popping up on the internet, blog posts, events, webinars, and so on. So IBM Model Asset Exchange, there's the link. I've encouraged you to go and check it out. We are always looking for people to collaborate with out in open source. If you want to chat about models that you would like to see on the exchange, you have research models that you would like to discuss to upload, interesting data sets, interesting use cases, please come and talk to me. Thank you.